Hey, this is lesson 14.4. We're going to start by talking about irrational numbers. It says a rational number is a number that can be written as the ratio of two integers. So it can be written like a fraction. That's where rational comes from, because you can write it as a ratio. An irrational number cannot be written as the ratio of two integers. So an irrational number is any number that cannot be written as a fraction. Obviously, pi is a very well-known irrational number because it doesn't end or repeat predictably as a decimal number. The square root of any whole number that is not a perfect square is irrational. So 4 is a perfect square. The square root of 4 is 2. 9 is a perfect square. The square root of 9 is 3. But 5, 6, 7, and 8, the four numbers that are in between 4 and 9 that are not perfect squares, if we try to take their square roots, the square root of 5, the square root of 6, the square root of 7, or the square root of 8, we get an irrational number. It's a number like pi that goes on and on and on and never ends and never repeats. The cube root of any integer that is not a perfect cube is also irrational. The decimal form of an irrational number neither terminates nor repeats. So here's the key idea here, and I really like this graphic they give us. Rational numbers and irrational numbers together form the set of real numbers. So we have everything that's here and everything that's here. Notice they don't overlap. There is no number that would be irrational and rational. There's nowhere that those overlap. But if you take all the rational numbers and all the irrational numbers together, we have all of our real numbers, which begs us to ask, what's not a real number? If we've got real numbers, then there's something else. And there is. It's called imaginary numbers, and we will not talk about those right now. But they are real things, but not like a unicorn or a dragon. They're actual numbers. So here we have all of our rational numbers. And remember when we talked about Venn diagrams like this before, if we were to imagine throwing a dart, and that dart went into this area right here, it would not only puncture this natural, it would go through whatever's behind it as well, whole, integer, and rational. So if I throw a dart into the natural, if there's a number that is natural, for instance, this 2 right here, and we'll talk about what natural means in a moment, but this 2, it's also a whole number, an integer, and a rational number. If I'm talking about this negative 2 right here, it would only be integer and rational, because if I threw a dart into this area, it does not go into these two. See that? So let's talk about what these are. Natural numbers, also known as counting numbers, are the first numbers that we learn when we're born. Well, not when we're born. I mean, I knew them when I was born, but it probably took you guys till you were 1 or 2. But 1, 2, 3, 4, 5, 6, 7, 8, 9, ... going on. 0 is not a natural number. Okay? And there are no decimals or fractions that belong in this natural group. It is a set of numbers that starts with 1 and then it goes up by 1. So 1, 2, 3, 4, 5. Whole numbers, the only difference between whole numbers and natural numbers is 0. So whole numbers are all of the natural numbers plus 0. And I remember that because 0 looks like a whole. It's a whole number. So natural numbers here, whole numbers are all of the natural numbers plus 0. When we talk about integers, a lot of times people think, well, when you say integer, you're talking about the negative numbers. And that's not necessarily true. We are including the negative numbers. This is what gets included, but we're also talking about all of the natural numbers and 0. So it looks like this. It's not just the negative numbers. That's just what's being added into the group now. Rational numbers are all the natural numbers, all the whole numbers, all the integers. And now with rational numbers, we're talking about all the fractional and decimal numbers in between the integers. Say, for instance, 1/2 or -2/3. 0.3 repeating, 2.25. Okay, those are all of these in this red over here, all rational numbers. Over here in this blue, irrational numbers would be pi, of course, any multiple of pi, any square root of a number that's not a perfect square. 2 is not a perfect square. A negative square root of not a perfect square. 3 is not a perfect square. And then the cubed root of anything that's not a perfect cube. So a perfect cube would be like 2 times 2 times 2 is 8, so 8 is a perfect cube. 3 times 3 times 3 is 27. 27 is a perfect cube, but 7 is not. So the cubed root of 7, irrational. For their examples down here, in example 1, we have to classify these real numbers. The first one is the square root of 12. Well, 12 is not a perfect square. So we're taking the square root of something that's not a perfect square, automatically an irrational number. And why? Because 12 is not a perfect square. Negative 0.25 with the 25 repeating. Well, it's repeating, so we're not going to be irrational now, so we're over into the rational. And anything that is a fraction or a decimal number just goes into rational here. It's not an integer, definitely not a whole number or a natural. It's just a rational number. And why? Because it's a repeating decimal. For C, negative the square root of 9. 9 is a perfect square because the square root of 9 is 3, so the answer to this would be negative 3. So let's look up here. Negative 3 does not fall into the natural counting numbers. It is not a whole number, but it is an integer. So if I threw a dart and went through this integer oval, it would also go through this rational oval. So integer, rational. Integer, rational, because negative the square root of 9 is equal to negative 3. 72 over 4. Well, 72 divided by 4 is 18. 18 is a natural number. We would get to it if we started at 1 and just started counting up, which means it's also a whole number, integer, and rational, because if I threw a dart and it went through there, it would also puncture this, this, and that. So it's all 4 of these. Natural, whole, integer, rational, because it's 18. And pi, of course, one of the most famous irrational numbers, because it doesn't terminate or repeat as a decimal. It neither terminates nor repeats. So that's their example here, and then they give us some on your own for us to do right here. On your own, number 1. And look at, they have got 0.121221222 ... What? Dot is a really good indicator that this goes on and on and on, but does not repeat. Remember, it would have a repeating bar over the numbers that repeated, and there is no repeating bar, and the ... lets you know that it's not going to terminate. So since this does not repeat, nor does it terminate, it is an irrational number. So for number 1, we would write irrational. Number 2, the negative square root of 196. Well, 196 is 14 squared. 14 squared is 196. So the square root of 196 is 14. And the negative square root of 196 would be negative 14, which means it's not a natural number or a whole number, but it is an integer and a rational number. So integer and rational. You need to put them both. Number 3, the cubed root of 2. Well, 2 is not a perfect cube. 8 is 2 times 2 times 2, so 8 is a perfect cube. The cubed root of 8 is 2, but the cubed root of 2 is something that's not a rational number. So the cubed root of 2 is irrational, because it goes on and on forever and never repeats. The next part of this lesson is approximating a square root. So let's look at their example here. Estimate the square root of 71 to the nearest integer for starters here. So for example 2a, The square root of 71 is approximately, remember that means approximately, not equal to. Because 71 is not a perfect square, well, we know it's irrational, but that's not what they're asking us right now. They want us to know that's the closest to what integer? It's going to be positive, obviously, so we're going to go with, let's see, 6, because 6 times 6 is 49. So 6 squared is 49. No, haha, 36. Just seeing if you were paying attention. 6 squared is 36. 7 squared is 49. 8 squared is 64. And 9 squared is 81. So we've got these squares. The square root of 71 falls somewhere in between 64 and 81. So it's not going to be 7 squared or 6 squared. But we are left with these two, either 8 squared or 9 squared. And we have to think, is 71 closer to 64 or 81? Well, it's 10 away from 81. 81 minus 71 is 10. And 71 minus 64 is 7. So it's closer to 64. Therefore, the square root of 71 is closer to 8 than it is to 9. But somewhere in between these two, but it's closer to 8 than it is to 9, because 71 is closer to 64 than it is to 81. The second part of the problem is to the nearest tenth. So this was kind of an easy problem because we know our squares of these numbers that they're asking us. But to the 10th, well, now that gets a little more tricky. So for part B, the square root of 71, we know is between 8 and 9. So we know it's either 8.1, 8.2, 8.3, 8.4, 8.5, and I could do 8.6, 8.7, 8.8, 8.9, but we know it's closer to 8 than it is to 9. So it's got to be on the front end of these 8.1. If we realized it was closer to 9, then we would have done the back end of these 8.6, 8.7, 8.8, 8.9. But we know it's on the front end because it's closer to 8. I like to pick right in the middle here, 8.3 times 8.3. 8.3 times 8.3. So 9, 24 with a 0, 24, 64, 65, 66. Oop. 9, 8, 8, 6. Two numbers behind the decimal, two numbers behind the decimal. So 8.3 would give us 68.89, and that's close. But I'm guessing 8.4 might be closer. So 8.4, we know it's going to be higher. There's no use in trying 8.2 or 8.1 at this point. 8 and 4/10. 4 times 4 is 16, 32, 33. 32, 64, 65, 66, 67. Add these up and I get a 6, a 5, a 0, and a 7. Two numbers behind the decimal, two numbers behind the decimal. Okay, I'm still under my 71, so now obviously I'm closer, very close indeed. But 8.3 doesn't make any sense at this point because 8.4 is closer. But still under. So now I'm going to try 8.5. 5 times 5 is 25, 42, 40, 64, 68. 5, 2, 12, 7. Two numbers behind the decimal, two numbers behind the decimal. 7.1, and in this case, let's think of it as like 71 is closer to 70.56 than it is to 72.25. We can do a subtraction and find out the difference between 71 and 70 and 5600ths is 0.44. The difference between 71 and 72.25 is 1.25. So the square root of 71 is closer to 8.4 than it is to 8.5. So we would put 8.4 8.4. So that's how we find to the nearest integer and then to the nearest tenth. And if we wanted, we could do the nearest hundredth, the nearest thousandth. The fun just continues. And if you've got nothing better to do today, I see no reason why you wouldn't just sit down and do a bazillion of these. It's good fun. Put away the video games. Let's look at their reasoning here. Make a table of numbers. Well, we did something like that. 7 squared, 8 squared, 9 squared, 10 squared. Square root of 71 comes between 8 and 9, just like we figured out. And it's closer to the 8 than it is to the 9. So to the nearest integer, they put 8. Make a table of the numbers between 8 and 9 whose squares are close to 71. So they did 8.3, 8.4, 8.5, and 8.6. Now 8.6 didn't make any sense because we knew it was going to be closer to 8 than it is to 9. So that wouldn't make any sense. Anything down here would make sense. They squared the numbers and found that 71 is closer to 70.56 than it is to 72.25, just like we did. So 8.4 is a better approximation than 8.5 to the square root of 71. Now we get to do some on our own. Yay! On your own. So let's look at the first on your own here, number 4. And it says to the integer and to the tenth again. So the square root of 8. Well, 1 squared is 1. 2 squared is 4. 3 squared is 9. So it's going to be in between here, 2 and 3, and obviously much closer to 3 than it is to the 2. So to the nearest integer, we'll put 3. For part B, we're going to have to pick the numbers between 2 and 3. Now we know it's closer to 3 than it is to 2, so we're not going to put 2.1 or 2.2, 2.3, 2.4, even 2.5, because look, it's so much closer to the 3. I'm going to put 2.8 and 2.9. Who knows? I might have to go down to 2.7, but I don't think so because 8 is so much closer to 9 than it is to 4. So 2.8 squared. And if you have a calculator at home and you're doing this on a calculator, I guess there's no harm in that, but I like to work them out. 8 times 8 is 64. 16, 22. 16, 4, 5, and we get 4, 8, 7, 2 numbers behind the decimal. So for this one, we get 7.84 for 2.8. That's pretty close to 8. Let's see what 9 is, see if it's any closer. So 2.9, 2.9. 9 times 9 is 81, 18, 26, 18, 4, 5, 1, 4, 8. Wow, both really close to 8. But if we did a subtraction to see who has the bigger difference, 8.41 minus 8 is 0.41, or 41 hundredths. 8.00 minus 7.84 is 0.16, or 16 hundredths. It is closer to 2.8 than it is to, it is closer to 7.84 than it is to 8.41. So 2.8 is a closer approximation for the square root of 8 to the nearest tenth. We get to do another. Number 5. The negative square root of 13. So I'm going to put my negative out here right now because sometimes I forget that negative somewhere in there. Well, 13 3 squared is 9. 4 squared is 16. So 3 squared is 9. 4 squared is 16. 13 is 4 away here, but it's only 3 away here. 4 is the right answer. And negative 4 because it was the negative square root. Now we get to do the to the nearest tenth. And it's between 3 and 4, a little closer to the 4. It wasn't like 15 and way closer to the 16 here. So it's going to be pretty close. Let's do 3.5 and 3.6. I think it'll be between those two. Who knows? We might have to do 3.7, but we'll see. Well, 3.5 times 3.5, 17, 15, 9, 10, 5, 2, 2, 1. Two numbers behind the decimal, 12.25 and 3.6. If you guess well, the best you can do is just have to do two of these. Okay, if we do this and it ends up being below 3.5, then I've got to do another one. Or if it's above this, whatever I get here, then I'll have to do 3.7. But if you can guess well, you'll have to do two of them. You won't get away with doing fewer than that. 6 times 6 is 36. 18, 19, 20, 21. 0. 18, 9, 10. 12.96. 13 is greater, so it did not fall between these two. It is so close to this one that I know it's going to be closer to this one than 3.7, but I've got to get where it's between the two numbers so I can be sure. Even though I'm sure now, I've got to be able to prove it. So 3.7 squared, 49, 21, 25, 21, 9, 10, 11, 9, 6, 3, 1. Two numbers behind the decimal, yeah. So 13 falls between 12.96 and 13.69. It's 69 hundredths away from here. It's only 4 hundredths away from here. So obviously this is the answer, 3.6. I'm glad I put my negative up here ahead of time because I would have forgotten it by now. Negative 3.6 is a better approximation to the negative square root of 13 than anything else when rounded to the nearest tenth. So the answer for number 5A was negative 4, and the answer to number 5B was negative 3.6. Looking at number 6, negative the square root of 24. Well, that's going to be between 4 squared, which is 16, and 5 squared, which is 25. Okay, it's obviously much closer to 5 squared because that's only 1 away, where here it would have been 8 away. So much closer to the negative square root of 24 is much closer to negative 5 than it is to negative 4. But it does fall between those two. Now that we have to go to the nearest tenth, and we know it's much closer to the 5 squared, we'll stick close to that. So negative square root of 24 is approximately negative, and we'll go with negative, and it's going to be between 4 and 5, much closer to the 5, so we'll try 4.8 and 4.9. I hope it's between those two. Let's try 4.8 and 4.8. So 64, 32, 38, 0, 32, 16, and 3 is 19. So we have 4, 0, 23.04. Not too shabby, but we'll see if we can get closer here. 4.9 times 4.9. So 9 times 9 is 81, 36, and 8 is 44, 0, 36 again, 16, 17, 18, 19, 5, 0, 4.2 decimal 24.05. So 5 hundredths away, 96 hundredths away. We'll go with 4.9, obviously. So the negative square root of 24 is approximately negative 4.9 when rounded to the nearest tenth. Number 7. A, we have the square root of 110. Well, the 10 squared is 100, and 11 squared is 121. So we're 10 away here, 11 away here. So it's approximately 10. It's a little bit closer to there. Since it's only a little bit closer, when we go to do this to the nearest tenth, we're going to stick near the middle, but closer to the 10. So let's try 10.4, and we'll see if we have to go up or down. It's going to be really close to this. Let's try 10.4 first. 10.4 squared, 4 and 4, 16, 4, 0, 0, 1, 0, 4, 6, 1, 8, 0, 1, two numbers, 108.16. So now we've got to go up to 10.5, so it'll be between those two. Had this been a little larger than 110, we would have gone down to 10.3 to see which one it's closer to, but we'll go up to 10.5. 25, 5, 0, 0, 105, 5, 2, 10, 1. Two numbers behind the decimal. Oh, close. So 110, here's 110.25, 25 hundredths away, and here 1 in 84 hundredths. So right here, to the nearest tenth would be 10.5. Make sure you're squiggly here for approximately 10.5. Well, the last part of the lesson is comparing real numbers. So which is greater, the square root of 5 or 2 2/3? So you'd have to estimate the square root of 5 to the nearest integer. And we know that that would be between, what, 2 squared is 4 and 3 squared is 9. So this is going to be closer to 2. Now you're going to have to graph these numbers. So it's approximately 2 and 2 2/3. Now we know it's closer to 2 than it is 3. So we know it's less than 2.5. And we know that 2.5 is less than 2 2/3. So we would say 2 2/3 is the greater. So you can see by estimating the square root of 5, we can compare these two rather quickly and easily. The trick is sometimes these will be negatives, and remember, when we're on the negative side, whatever number is closer to 0 is the larger of the two numbers. Excellent. So now you can head over to the next video and do the journal page 340, which is for lesson 14.4.